Yeah.
Yeah.
Yeah, that's the first year.
I want to start sending out just sending those three tests afterwards. So I think we can do that, because we can for testing the game.
You're in test next week?
No, no, it's usually after. Probably after. I'm assuming it's gonna be the same if we got like the test for,
No.
we can do it now that it makes sense to me. Oh my goodness, what happened? This is so weird. Now we see why.
Remind me of the sun. Sin X times 1 plus
Oh, I tried it one day, not the identity, it's one of the, is that the double?
yeah, I think
And the identities are, oh, it might have been identity actually. The identity is sine squared minus 1 is equal to cosine squared. And tangent is F dot tangent squared. Yeah. Oh, it's no different, it's not. It's hard about that. At least the test, I want to make myself Excel spreadsheet and just list what it is I do for jobs. And I know exactly when to start. It's a little overkill, but I'm going to review it. So, and because I need all the other jobs. Five, and I screwed around.
All right, welcome. So let's go over some announcements before we head into lecture. And so, of course, the big announcement is that we have our midterm next week on Halloween. Yeah, that's pretty scary. So the midterm is going to be on Thursday. Just again, email me if you need to do some other arrangement. And then we'll review on Tuesday. So that'll be a good chance to recap, ask more questions, and get clarity on what's going to be on the exam. And so other things. So I'm going to try to hand back all your papers. So I'm working on that. Also, if you missed the quiz, get that made up ASAP. So ideally, if you missed the quiz, you should email me and let me know that you are missing it so then we can make arrangements that day. And then if you, yeah, so just get those quizzes fixed ASAP. That's not a problem. But I don't want to kind of linger on, and eventually I might cut off makeups for quizzes, but if it becomes an issue. I'll also hand back popcorn labs, at least the ones that are complete. I think a few people turn them in at the last minute that I haven't gotten to, but then there are others that like handed me piecemeal things. So if you thought you turned something in but you don't get it back, and it hasn't been graded in the grade book, it's probably because something is missing, so maybe double check with me. There's a few that I just have either like an abstract and no lab or vice versa. So I haven't like graded those yet until I figure out what's going on. So come talk to me about that. I haven't graded anyone's lab 2 yet, so I'm slowly falling behind but trying to catch back up this week. So, oh, sorry, lots of announcements today. So today, so unfortunately I didn't know about this till today, and it is during our class time. But maybe you could sneak on since it's also on Zoom, or so you could check in, after class ends. It's also in 129, so you could just, pop on over after class. But this is an information session for the Ford Family Foundation Scholarship Program. So very prestigious program. I encourage everyone to apply. There's lots of money involved with that. And of course, at least grab some pizza today after class, if nothing else. Right, trying to think. Oh, one other. So when I hand back your lab, so there was a small incident at home. So basically how it went is I walked away from your papers of nicely graded popcorn labs. I looked back and there was blood on them. So my cat had a nosebleed and for some reason wanted to, share the nosebleed with everybody. So I hope that makes you feel slightly better, that at least it wasn't my blood, it was my cat's blood. So it's not human blood, but it kind of sprayed everywhere. So if there's weird spots, I apologize. Yeah, and my cat's like never gotten a nosebleed before. So that's my cat excuse for the day. All right, I think that's all for announcements. So lab is at the back. So flame test this week. So make sure you wear your cotton clothing, closed-toed shoes, all that good stuff. All right, so let's continue on. So just a quick recap of kind of where we were and what where we're going. And so we had said, okay, we have this thing called light with our electromagnetic spectrum. And again, the key points kind of being how fast these electromagnetic waves move. Okay, so now we're kind of characterizing them. And so now we can look at kind of the full electromagnetic spectrum. And so some things to take note. So it's arranged with our low frequency on the left, high frequency on the right, which also corresponds to increasing energy. So of course, low energy with low frequency. And then you can start to piece together what that corresponds to. So radio waves tend to be long. And then you also see that in the wavelength. So again, all these characteristics, are interrelated. You can always go back right, to this formula here. So if you don't already have that written down big, right, do it again. And remember that little v was frequency, so it's not speed, right? So this is frequency, and we said that was in hertz. And remember, this was wavelength, and we said it should be in meters. And so now we can see how that relationship kind of tracks along. And so again, right, orient yourselves, radio waves down here. Obviously, those AM waves are going to be longer, so that's why AM can travel so far. And then, so smaller wavelengths are TV, FM, cell, and then I forget exactly where like 5G comes into play as well, so it would also be there. And so part of like, you know, the controversy with it, so of course 5G, you know, it has to have a lot of repeaters everywhere, right? And so why it has to have a lot of repeaters is because it doesn't travel as far. So right now you have all these repeaters, but of course, right, there's a lot of controversy over like how much exposure people are getting. And so that kind of goes into like research, and it's actually really hard to, of course, right, try to quantify how much exposure we're getting to any of these electromagnetic waves. So that's always why, you know, there's so much controversy over that. And of course, microwave, so also now we're getting shorter. Of course, microwave, right, they just kind of excite those water molecules to heat up your food. And then we have our infrared, so right just under our visible light, so longer wavelength. And then we see, of course, blown up our visible spectrum. And so this is also kind of good to keep in mind, right, especially when we talk about the hydrogen atom next and what we talk about. Because when we look at kind of our spectral lines, we're mainly just looking at, of course, our visible region, right? So we're just looking at that small region. And so it's really small, right, when you look at it in terms of this electromagnetic spectrum. And so it's only from 750 nanometers to 400 nanometers, which, again, red. And back to the rainbow, we have this Roy G. Biv, and so that goes in order of energy, and so decreasing wavelength, so right, red is the longest, violet is the shortest. So pretty small section there. And then of course higher energy is going to be ultraviolet, and so obviously, right, we can't see that, and that's a lot of, again, organic compounds. And so eventually we'll look at like TLCs and what that is, but we're going to find that you're going to have to illuminate them with a UV light, because organic compounds have all their transitions in the ultraviolet, which is why they appear colorless. And so now we're starting to get into colors. And then, of course, obviously, as we go across, now we have even higher energy, shorter wavelengths like X-ray, and then even, of course, right, destructive gamma rays, so extremely high energy. And so again, it's emphasizing that this is a really small region. So again, just kind of keep that in mind. We'll revisit that. So again, we saw how they're arranged. So this might be something you do in an exam, you know, which one has a longer wavelength, which one has a shorter one, those sorts of questions. And then, of course, just to re-emphasize this, that these high energy electromagnetic radiations can start to, of course, damage biological molecules, right? They can cause DNA damage and all sorts of issues. All right, so let's talk about, well, what is the atomic spectrum, right? So what are we looking at? And so we can think about several different things, but what's happening? Does anybody know? We have to think about it. What happens when you have like fireworks and neon lights? What are you seeing? What kind of describe it? What's going on? Yeah. Yeah, but but it's even like more simple than that, because we want to think about, well, what's the light coming from? So it's the electrons, so it's not moving in though, but relaxing out. So right, we have to think about, well, what are these processes doing, and kind of roughly what's happening. And so we usually just look at hydrogen, and so we can kind of take, right, our Bohr model approach, so n equals 1, right, n equals 2, blah, 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 continuing. And so, right, we have our electron, let's just say, in our ground state. And then, so what's happening, and again, just different sources of energy, right? So you're saying, well, what happens when we absorb that energy? So we're going to do that today in lab in the form of heat. You'll be adding some energy. Or we actually will also do the spectrum tubes. We have a lot of tubes. And so, right, you could also pass electricity, such as neon lights, right? Those are so nice. But what is that? So what you're doing is, right, you're adding energy to that electron. And then that electron is going somewhere, right? So then it gets promoted to some higher energy state. But then once it relaxes back down to the ground state, that relaxation is what gives off that light. So that's pretty important. So, right, just kind of think of that. So now you can think of all the pretty colors. And so now we're getting into kind of why things are certain colors, but I want to slow down because I'll get excited too. And so now we have to understand, well, what are we looking at when we're trying to visualize this emission spectrum? And I was debating whether to drag the hydrogen lamp, and maybe I should have dragged it. All right, so right, you have this like hydrogen lamp. So you're passing electricity through that. And then, so the question is, okay, well, it has this overall color. Again, you'll see this in lab. And so it's kind of this pink purplish. And so we have to understand, well, what that prism is doing. So then it goes back to, well, we have to first understand that just normal white light comprises a full spectrum, right? So do we understand that? So we have, again, going back to our electromagnetic spectrum, we can look at our light. Again, we'll do this in lab, so it'll make a little bit more sense. You can look at our white light on our little prism, our little spectrophotometer, and we'll see the entire rainbow kind of light up. So that's for white light. So how we kind of identify molecules then in outer space is, well, then we can, right, look at their spectrum. So this emitted light, which is, of course, characteristic for each atom. So it's passed through a prism, and then it separates that into this unique pattern of wavelengths. And so depending on what you're looking at, so if you're looking at the emission spectrum, that's going to be what's lit up. And sometimes you also see an absorption spectrum in other cases, but then it'll be blackened lines. So it basically gives the same information. It's just the emission, they're lit up. On the absorption, it'd be the entire rainbow with the ones that it's absorbing blackened out. So same data though. And so right now the key point is, okay, well, now each line spectra, right, can be used to identify elements. So that's how we can look at the stars and all the, right, the nebula, everything. We know, okay, these are what elements in there. This is, you know, what elements dominate certain stars. So that's useful. And so each of these are like its own fingerprint. And so in lab, we have a really nice periodic table that has every single spectral line of all the atoms. So that's nice to look at for reference. So again, you can kind of get the sense of the fingerprint. And so now here it is for hydrogen. Again, showing what we see. So again, our hydrogen lamp is lit up this pink purpley, passes through the slit, which again, we have this in our lab. Then it'll get separated, and you'll kind of look off to the side. Unfortunately, our little devices have pretty poor resolution, but you can still kind of get the idea. And then so we're looking at this. And so they have 4 lines. I kind of think it's more 6, but anyways, you can debate that later amongst yourself. And so again, here's different variations. So here's our emission spectrums. And so these are kind of absorption spectrums where they're rayed out. But again, same data. And so now let's understand though, okay, well, what are we looking at? And so there's a lot of things that we're kind of getting at with this concept. And so actually I'm going to pull up some other piece of data. And so kind of the big thing too is that they're trying to calculate that everything is quantized. We're getting again towards this whole energy level idea. And so the other thing to kind of note is when we're looking at our little hydrogen spectrum on the visible region, and so I like this graph from Wikipedia because it gives us a nice idea. But again, note our visible region is pretty small, so it's only a few of those transitions. Now, from our side, we don't necessarily know what those transitions are right now. So, that's where we have to calculate it. So we're kind of getting there. But this is, kind of what we're studying. And so what we kind of have to think about before we even get into, what they translate to is what we're seeing is every possibility, right? So when we talk about excited states, so again, we've taken an oversimplified approach right now. So we're just looking at our Bohr onion model. And then you have to think of every allowed transition, right? So like 1 to 2, 1 to 3, 1 to 4, blah, 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 right? So look at all these relaxations. And so you can kind of see, so this is pointing out, these are the ones that correspond to the visible region. Again, you wouldn't know that these are the transitions. That's not the point. The point is to say that there are also transitions everywhere else, right? So literally every possible configuration is mapped out and possible. So that's what's shown in this scale, every little possible transition that they have kind of mapped out. And then, so with that, so they're trying to, again, understand that this energy was quantized, and we'll get back into this kind of packets and energy level. And so then, the energy is somewhat related to the position of the atoms, again, how far it out is from the nucleus. And then quantize, again, that's why we're getting to these energy levels, and I'm saying n equals 1, n equals 2, etc. in these discrete whole numbers, that's what they were discovering back in the day, is that you have to have a certain energy transition that corresponds to some allowed transition. And so again, we're looking at it from the Bohr model. So things start to get very complicated very quickly once you have more than one electron. And so even when you kind of simplify these higher analogs, you still just say that they have one electron, since it gets, again, very complicated. And so, again, our Bohr model, we kind of have this fixed orbit idea at this fixed distance. And so, again, the energy of our electron is proportional from the distance to the orbit. So again, kind of calculating the energy. And so I will say, if you want a deeper dive into this, I posted on Blackboard this atomic spectra and atomic structure. So that kind of walks through a little bit more in detail kind of how these calculations are made behind the scenes, so you can kind of appreciate that. And so again, here's kind of our oversimplified model now. So looking at what makes these colored transitions. And so again, now it's just saying that the energy that corresponds to this transition, so the electron going from our third energy level to our second, is then equal to this wavelength, right? So that's, again, where we're seeing that quantized packet, since now we can quantify how much energy this is. And so our energies, so now we're getting into, again, our principal quantum number. Again, we're taking our oversimplified kind of Bohr approach for all of these. And so our energies are defined as being negative, so lower is more negative, but also more favorable. And so an electron with an energy equals 0, that's when it's escaping then from the atom. And so again, as n gets larger, so we have two things occurring. So the amount of energy between each orbital gets smaller. So remember I mentioned that where each successive energy level gets smaller and smaller and smaller. And the energy of the orbital becomes greater. So it's just increasing in energy. Right, so again, that's just going back to our basic principles of how we've filled up our electron shells. We just have kind of re-simplified it to our onion approach. And so, right, it's saying we go further and further out, so that's higher energy, more positive. And so then we have some forms of our equations. And so now we have this important one, where basically our energy then is equal to, so negative 2.18 times 10 to the negative 18 joules times 1 over n squared. So that's for each energy level. And then, of course, you could also calculate your transitions. Yeah, Keenan. Yeah, it's already on there with the live link. And so now we get to our next formula, right? So now we can take this formula, and well, if we want to figure out our energy difference, right? So we're trying to calculate, eventually we're trying to calculate this. So now we can say, well, our difference in energy then is equal to negative 2.18 times 10 to the negative 18 joules times 1 over our NF squared minus our initial squared. And so the final one should be the lower number, because again, right, you're always looking at that relaxation and transition, but it ultimately won't matter too much. You'll just kind of have to watch your sign, because again, it's mainly about that difference.
So can you say that's the transition of the energy?
Yeah, so this would give you your change in energy, right? So what we're trying to translate here is that each energy transition, right, it's quantized, so it has to be at a certain energy, it has to be a certain number. That's why we just have all these discrete whole numbers. And so again, right, it's reflected in here. And so again, how they came to this conclusion of this quantized model is we go to the photoelectric effect. And so what this is, well, right, again, they're trying to understand how light works, how energy works. And so the idea is, okay, let's shoot this beam at this piece of metal. So they're trying to do that. And, right, let's just say that they were shooting a red laser, because that's going to be lower energy. And so they're shooting this red laser at this piece of metal, right? They can increase the beam intensity. Nothing happens, right? It just stares at them. But then now let's say they shift to a blue laser. So now they hit a blue laser at it, and boom. Now all of a sudden for some reason, right, that's ejecting photons. And so, okay, what does that tell us, right? And so now let's break this down. And so again, from our kind of classical theory, how we expect things to work, right, from classical mechanics. It should be, we apply more force, right, we add more hose to it, and we expect it to make a difference, right? So classical theory states that if our wavelength of light is made shorter, then more electrons should be ejected, right? So it's saying that it should be proportional to the amplitude.
Can you say that again? I'm sorry, I couldn't hear properly.
Yeah, so basically, right, what we're saying is, well, by classical theory, that if we shine more light at it, right, it should go. So kind of like think, if we're just thinking classically a hose, right, you're shooting water at it, okay, let's shoot more water, okay, now it should force it to go, right? But that's not what happened. So it's suggesting that, right, let's say you use a dim source, again, thinking of like a small trickle of water, it would just take a while to go. But that's not what happened. So this photoelectric effect, again, tells us that there's some sort of energy levels that are quantized. And so that means that really you have to meet a threshold frequency then. So that's, again, the key, right? So it doesn't matter what sort of intensity light, right? It just matters that it's a correct frequency. And so it mentions this, that even, right, a high frequency light, so saying a blue light from a dim source, right, would then still cause the electrons to be ejected without any lag time. So it's not about how dim it is, but the frequency. So right, maybe say that. So frequency, which again will relate to energy, is what's important. So again, right, we're saying it has to have the right wavelength to make that correct transition, right, that corresponds to a certain energy. So that's all that we're getting at. So it doesn't matter how much red light we shine, right? It's not the correct frequency, so it's not going to work. And so then this is where the whole kind of idea as little photons comes into play then. And so this is an important formula. And so now our energy is considered to be in kind of little packets of light that travel in a wave. And so we can also rewrite that as this. So energy is equal to, and I still need to define it. So Planck's constant is 6.626 times 10 to the negative 34th. And notice you're in joule seconds. Yeah.
Is that energy equals H times V or H sub V?
H times V. So Planck's constant times the frequency, right? But then we could go back to this formula. So frequency equals C over wavelength. So I'll just kind of put that. So frequency equals C over wavelength. So from this, right, you can just rearrange and get this formula. So they're all related. Does that make sense? So that's how you get this one, which may be a more useful form for our kind of word problems that we'll encounter. And so again, right, Planck's constant, it's in joules, or joule seconds. Obviously, speed of light, meters per second. That means your wavelength. Make sure that it is in meters before you do the calculation, because it's probably going to be given to you in nanometers. All right, so this means, right, so now we're kind of seeing where this is going. So, right, we're headed there. But basically, okay, well, if we can calculate the energy of these transitions, then we can get our energy, right? And then we can plug our energy into this formula and see what is the appropriate corresponding wavelength. So we'll be doing that. And so again, right, that's really key. So that's how you can back calculate what energy transitions everything corresponds to.
Can I just clarify, make sure I understand? So the one diagram that you have for the hydrogen,
Well,
or the next?
yeah, well, not even think more simply than orbitals right now, because we've gone back down from like orbitals to just onion rings. So yeah, just principal quantum energy levels. So yeah, it's whatever point, right? So you can just arbitrarily take, it looks like this is 6 to 2. So if we were to do this calculation, right, 1 over 2 squared minus 1 over 6 squared, calculate that, that should correspond to this transition.
Okay, so that's the energy it takes from one transition to the next.
Yeah, so that means, okay, that's what you're seeing. And so kind of, and again, I'm not trying to like overwhelm people, but why I like this book is what they've calculated, at least on this one, is showing you again all the transitions. So this is just for hydrogen, and right, so they've kind of calculated all these possible ones. And again, kind of what goes beyond the scope of this course, but kind of where we're teasing into is that they talk about, you know, forbidden transitions, which goes into like spin states, which is, again, where we're headed, but you can kind of see where this is good basic knowledge. So yeah, basically what somebody did at some point and how they get these formulas is, okay, they start trying to calculate like literally every possible transition. What is that energy? Where is it on the diagram? And so maybe the Wikipedia one is a little more clear.
And then the transition, when it's something like we can see on the spectrum, that's what did you call it?
Yeah, so that's the relaxation, right? So when the electron goes back down, right, energy is being released. So again, right, there's that change of energy. So we can quantify that energy that's being released as it relaxes back down. And then, yeah, we don't know, right, just offhand which transitions they correspond to, but we can kind of calculate that out, yeah.
For the atomic spectra and atomic structure handout, or like that, is there a section in there that you would recommend for us to go over, or sort of highlight to kind of better understand what we're talking about with these ionization?
Just kind of like starting from the beginning, like if you just start reading, but it is pretty dense, right? So you don't necessarily like need to understand it, but you can kind of piece like how they came through these calculations, you know, you can kind of see the math and appreciate it to understand, you know, how they took all these things that we've been kind of talking about, effective charges, right, distance from the nucleus. So they take all these calculations and start translating it to this data. So it's kind of powerful. Campbell.
So this energy is like the electron actually moving a distance from
Right.
the nucleus, not just changing like its speed or whatever.
Yeah, so you're just watching it go from one energy level to the next, and then, right, our job is to maybe try to quantify that, yeah, but we're just like seeing the pretty picture at some point, yeah.
What's this book called again?
It's online, it's like atomic spectra, but again, it's pretty dense. Like the book is dense, but it's kind of to show you where this is going and how people have teased this out. All right, so where were we? All right, so now we'll do some math with that. So let's look at other things that we can quantify. And so now we have this sort of proposal. Okay, well now we're trying to figure out, again, how does this little packet behave like a wave? So then de Broglie came up with this proposition that basically everything has some sort of wave. It's just that our wave is insignificant compared to us, that it doesn't matter. So we'll calculate that. And he said that it does matter, though, for a small particle, since it's going to be at the same scale. So we'll, again, prove this. And so because it's so small, then the wave character of the electron is significant for that electron. So let's go ahead and calculate that. So let's go through this formula. So now this is your de Broglie wavelength here. So that's this little symbol is equal to, so Planck's constant divided by, so mass, so we have to remember that this is physics world, so mass has to be in kilogram, and speed is going to be in meters per second. And so now let's compare the calculations. So do two things for me. So I want to know the wavelength of a person. So let's do, I don't know how much, let's do a 100-kilogram person. And they're moving, let's just say 1 meter per second. So find that person's de Broglie wavelength. And while you're doing that, compare that then to an electron. So I'll give you that the mass of an electron is 9.109 times 10 to the negative 31 kilograms. And an electron will move just under the speed of light, so probably 5.6 times 10 to the 6 meters per second there. So give me those two calculations. Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And it is up on the notes, but then I'll try to hand out some more quizzes. Uh, 9.109 times 10 to the negative 31. Well, I know that, but I have two quizzes. I don't have quiz for you. That's what I was thinking. Well, I put that here.
Okay, I got it. I got it.
Okay, well, I have to revisit that. All right, do we have an answer, or are we still working? Okay, maybe we need more time. You can post answers in the chat. All right, so let's hear how it's going. So let's start with the person. So we're trying to solve our wavelength equal to our Planck's constant. So just double checking my units. So kilograms is fine. And 1 meter per second. Cool. And so what do we get for this answer? Yeah. That sounds correct, so I'll punch that in. Doing some mental math. So yeah, something pretty tiny. Okay, so that's in meters, right? So 6.626 times 10 to the negative 36 meters for our wavelength. Pretty small. Okay, so that kind of makes sense why probably not significant for us, right? That's pretty small compared to how big we are. So now let's try the electrons. So what do we get for the electrons? Now we do same process. Over our mass times our speed. Anybody want to yell at an answer? Make sure you put everything in parentheses. So now I get this for the wavelength. So 1.2, well, I guess we can round it to 1.30 times 10 to the negative 18 meters. $10. So, right, still pretty small, but then what's the scale of the electron, right? It's going to be on that scale of nanometers. We could convert it to nanometers since that's kind of the atomic scale. So, right, so 0.129 nanometers. And so that is relevant, though, right? So even though that's still pretty tiny, it's bigger than our de Broglie wavelength and about on the scale of the atom. So pretty small. So, right, our atom is going to be on this scale, so roughly. So that's why our de Broglie wavelength is relevant. All right, so that's kind of explaining our behavior. This is probably a good spot for a break. So let's go ahead and take our break, and then we'll start chapter 5 then, which again is going to keep building upon this. And chapter 5 should be linked.
We were trying to do chapter 4, and we were wondering where you got the numbers, these numbers right here. Like where you got the 3.0.
So that's the speed of light.
That's the speed of light?
Yeah, 3.0 times 10 to the 8th meters per second. So that's always,
in the speed of light?
yeah.
And then you just do that over that to get to the wavelength. Okay. And then the energy, I know that you do the H times the V. Where do you get the H?
It's always Planck's constant. So it's always 6.626.
626 times. Okay. So energy is always that, and then, energy is always, H is always Planck's constant. Okay. And then what was it, 3.001 again?
Speed of light.
Speed of light and Planck's constant.
It's like yeah,
I actually have a state from
Okay, pizza just showed up for the other event.
So, yeah, starting Tuesday, Thanksgiving week, I'll be traveling.
Yes, and then you just want to try to keep up on the lecture material. You can of course watch online.
You think we have enough time in the break still to go get like some pizza?
Probably, since it's right next door. Yeah, so we still probably have like 5 minutes. Yeah, you gotta bring them.
I'm sorry.
I start sitting on your lab.
Econ's another one, it's kind of like physics in the way that you really need calculus to understand it. The algebra
So you gotta
didn't make sense.
narrow down.
201 is pretty easy. It's just like so dry. If you don't practice it times, you can bring it and it's good by car. No, never allowed. There's like 6 people on.
I know that Oregon's micro
We'll see if we have time.
I think mine was on English, did you not, the abstract, isn't it, statement?
Maybe,
Okay, I'll
So-
read it out for you.
yeah. Or I have to look at my pile and see.
Yeah, I took psychology 201. or less than or strategic oriented. We want to more microbiology. And I think there's a question to do. It was fun. I like psychology. I got to eat it.
My sister got
I could, I am taking
Getting a bachelor's in psychology, but that's one of those bachelor's ones. And I just want to go on.
You need to have for those that you can't have masters. And it's also she's like, I really need to go back to school.
Physics is kind of the same way. Like, I was trying to physics guy, physics related. You need a math.
Yeah, my question
No.
Yeah, there's one that get rejected.
My brother's been after all this time, but he doesn't have That's why I was just your committer's a lot.
It's okay, you'll have to,
All right, did we all make it back from break time? All right, so let's continue here. And so again, right, this is building upon what we were just talking about, right? So we're still trying to understand, well, what is this wave? What is this light source, right? Is it a wave? Is it a particle? So this was, again, right, huge debate around Einstein's time. And so, okay, now let's talk about this double slit experiment. And so the question is, okay, well, let's say the electrons are a particle then. And so just like throwing a tennis ball or a ping pong ball, right, you throw the ball through the slit, and then if, you know, let's say you put ink on the ball and just kind of throw it and see the spot pattern. So we would expect it to just hit directly, right, just go through the slit. It's a particle, so we think. And so what they actually found, and what was shocking, is, okay, right, they passed it through this double slit here, but then they got this weird interference pattern, right? So they got this pattern of extremely bright spots and then extremely dark spots, so kind of this alternating behavior. And so that interference pattern, though, showed that it was behaving like a wave, right, since it can travel kind of beyond this slit. So again, right, we're thinking how a particle would just hit directly, but then this wave can kind of go beyond that. So, okay, well, that was interesting. And so now we start getting to this concept, and really where we are today is, right, this wave-particle duality, and then also this uncertainty principle. And so again, right, we're trying to characterize how does this electron behave. So, right, we can try to characterize it like a particle. So if it's a particle, well, we can measure the mass of it, right? Its mass. We could also get its position, right? You should be able to tell its position. And we could also note, right, its wavelength, its frequency, so we can characterize that. We can see its interference pattern. But now here is the problem, right, is we cannot observe both properties simultaneously. So the problem is, as soon as we try to measure the position, right now we've perturbed it. So we cannot just observe the electron. And so, right, this again goes back to how sensitive the electron is, right? You shine a light at it, now it's perturbed. And so now we can say, okay, well, how certain can we know this? And so basically, we can try to measure these two properties. So either its position or its momentum or velocity. And so sometimes, right, you might see this rewritten as momentum. So mass times velocity is momentum. Remember that from physics. So if you see that in a different form, that's what it's getting at. So delta P, or delta X, delta P. And so now we're saying that we can know this to a certainty basically within this margin of error, where H is Planck's constant again, and then over 4 pi. So basically, right, the more accurately we know the position, then the less we know about the speed and vice versa. Because again, right, anytime you try to measure one, now you perturb the other property. So if you measure the position right now, you've messed up the speed. So that's where the uncertainty comes into. And so, right, this starts getting into our orbitals. And so again, looking at kind of our classical mechanics, we can map out the trajectory, right? So maybe you've done this in physics, right? You can launch a ball multiple times, you can predict its path. And so, right, again, it has a predictable future. You know, stunt guys do this all the time, right? You can take your motorcycle, calculate whatever velocity you need to make the cool jumps. Wasn't there like a local Evel Knievel like jumping off of the Sizzlers in Grants Pass or something? I saw like a crazy news article. Anyways, right, but it's the same sort of concept. You calculate your trajectory. And so the problem starts coming into play, and this is where our orbitals are starting to be born, is, well, right, we can't know our position and velocity. We can only kind of predict where it will be, and really it becomes this probability density map. So now, right, the best we can do is at least describe the region that it will be in. And so this is just kind of our comparison now. So again, right, classical mechanics would say, okay, we can outline this trajectory. We can know where our little junior Evel Knievel will land versus the electron. Well, we know it's somewhere along this line. Not entirely sure where, but this is where it is. And so you're starting to get into this shading aspect too, where you notice, right, this darker line kind of in the center here, kind of following our classical trajectory. That's showing that it's highly probable that the electron is somewhere right along this path. But then notice as it kind of gets this lighter shading, right, it's saying, well, it's still possible that the electron could be over here, but not as probable, so that's why it has this kind of less darker shading. So again, right, this is where we're getting our probability density map. And so now this goes into Schrodinger's equation. And so, right, again, the point of the class is not to, do the math behind it, it's to take the nice, pretty picture approximate approach to it. And so, right, what computational chemistry is ultimately attempting to do is, of course, solve for this. So this goes into, right, that Schrodinger's equation is too complicated to solve, even for hydrogen. So you just had to make approximations. And so it says here, again, we're just kind of appreciating this. So solutions to our Schrodinger's equation produce our wave functions. And then what we're actually graphing is then our wave function squared, which is how we get our pretty pictures. Right, so that just gives us our pretty pictures. Yay, so right, you could take much higher level courses that kind of try to go into this, but this is all we want to take away. That's how we know what these orbitals look like now, right? We're just appreciating the results, and then again, how to take the oversimplification of that. And so now we're kind of reintroducing our orbitals, but now kind of more properly, and then defining them as our probability density function. So again, right, it's telling us the probability of finding an electron at that particular point. And so this is, again, how we get the shape of our 1s orbital. So you can note, of course, lots of electron density out here, and then starts to drop off right once we kind of get to that radius. And so now here's just another mapping of it, again, plotting our wave function squared as a function of r. So notice again where it drops off. That tells us kind of where our first shell is. So that's our 1s. And so now, again, we can tell where these shells drop off. So right, this radial distribution function, all we're saying is, okay, right at this point, this is kind of where the maximum probability is, and then it goes out from the nucleus all the way to here and kind of drops off. Right, so now this is saying from this plot that the most probable distance of our electron in our 1s orbital is about 52.9 picometers.
Overlay the second shell, S2X on there, would it be another spike next to it? Because it has a higher energy level? And then would go down again? Like if you were to...
Yeah, so let's look at that. So right now you're kind of seeing, okay, this is where the onion rings come back into play. So yeah, so now we're looking at, just like you're saying, okay, here's our 1s, right? There's our node. So now we can say, that's why we say there's a node between our onion rings. So yes, right? So there's our first spike. It's kind of not shown very well. There's our node. And then yes, right, there's our second energy level, just like you're saying with a spike there. And then, of course, they start to get more diffuse. So you can already tell that already by this graph, right? So even just the scaling, so that's just the 1s, right? And then, okay, mapping our next node, our next energy level, it's already pretty off scale. So does that kind of make sense? And so then, right, kind of building up, so now we're just focusing on our S onion rings right now since they're easier to visualize. So same thing, so our 3s, right now there has 2 nodes to get to our 3s. Again, I like this, right? So again, map it out, our 1s, there's our node, 2s, there's our next node, now there's our 3s there. So again, you can see that plotted out. So it starts to get, right, more diffuse too, so you can kind of appreciate that. So let me flip back. Okay, nothing else on there. And so now we get into these quantum numbers. And so these quantum numbers, we just kind of want to pair them to what we've already talked about. And so these quantum numbers, too, we can kind of think about them as coordinates. So they're just, again, other ways to describe where our electron is located. And so we notice that we also have our quantum numbers, so they're based off of certain values. And so we've already kind of looked at this principal quantum energy number. So that's just our n, again, corresponding to our basic Bohr model. But then we'll kind of look at these and relate them to what we've already discussed. So we'll do that. And so again, just recap, we have our Princeton quantum energy number, so N, so that just corresponds to each energy level. So it starts at 1, and it's just telling us, okay, it can be any whole number integer. And then, of course, right, we've kind of seen this. We're re-emphasizing. So, of course, the larger the value of N, the more energy the orbital has. And, of course, the larger the orbital, right? We're seeing that as we get further and further out. And so as we look at it, so right now, the little L's correspond to the orbitals. And so now the L's, and you might want to flip over to kind of the next page as well, because your book has a really nice summary of all this. So right now, we're kind of recapping, okay, we're at the first energy level. And then remember, we only said, well, the first energy level, the 1s, is the only thing allowed, right? So there's only an s orbital. And so that's what's shown here. And so our s orbital, any s's, have an L of 0. Oh. So write that down. So that's also shown here. So anytime L equals 0, okay, that's saying that your electron is in the s orbital. And so this is where the coordinate system starts coming into play. So you have N equals 1, so that's first energy level. L equals 0, so I know that's in the s. And so like we've kind of covered, so it's the lowest energy level, right? We could go back, and this is where you might want to go back to the P table, and again, just kind of repair everything, right? Because we kind of want to take our electron configuration and what we've gathered so far about the structure of the periodic table, and then kind of relay our quantum numbers on here, right? So again, you're looking, we can go to our electrons. Okay, we're filling up, right, our first energy level, our 1s, that's corresponding to our hydrogen, helium. And then this nodes is just saying, right, how many nodes it has. So of course, n minus 1, so the first energy level, right, it's just the ball, so it has no nodes yet. And nodes, right, is again just an area of no electron density. And so we saw this, so that's good, right? That's starting to hopefully make sense. And so again, just similar graphs showing slightly different information. So right, this is our wave function squared versus our radial probability. So again, showing us where the most electron density is. So this is be our first energy level, right? That would be kind of like our radius. Second energy level, right? That would be, again, our radius probably for our atom, whatever we're looking at. So then it just kind of continues. You can see again where that radius is shifting out. Again, note the nodes, right? So you have 2 nodes for the 3s, yeah.
For the electrons that end up being in the different radiuses, what kind of like determines that? Is that like the electrons all have different energy levels, or are all the electrons have the same energy level?
Well, so that's the thing, right? So we're saying that everything, right, all these energy levels exist, right? They're all accessible. But then what we're trying to figure out, and so kind of your question is, and it could be several different answers, right? Because it could be, well, are we trying to figure out like where our electron is jumping from, right? So then we're focusing on transitions. Or are we trying to, and what this is more mapping is like our orbitals. So trying to figure out what are our valence electrons and how are they interacting. So kind of different questions sometimes. Did that, I don't know if that helped. All right, so then now we're getting into, again, our angular momentum quantum number, so our L. So again, our L is just telling us what the shape looks like. And so now L can have values from 0 to n minus 1. But again, the key thing is to remember just what they correspond to. So if L is 0, that means it's our s orbital. Once we get to L is 1, then we have our p orbitals. L equals 2 will correspond to D, and then L equals 3 signifies F. And so then we can, right, just kind of continue with our quantum numbers. And so now we can figure out kind of the next one. And so first it's kind of saying, okay, let's look at our p orbitals. And so, right, well, we have 3 p orbitals. And now we have our next quantum number, our m sub L. And so this m sub L formula is equal to negative L, and then integer value 0 plus L. But again, just kind of figure out how to derive this. So I think this chart is easier to see. So now we can see, okay, well we have, and let's look at our second energy level now. Okay, second energy level. So you can have a 2s is allowed and a 2p, right? So that's this one right here. Okay, so if my L is 0, but my n is 2, then that's looking at something here. And then, right, S, well, if L is 0, then M sub L also has to be 0 for S, but there's only one of them, so that also kind of makes sense. Now, for our P's, well, we said, well, L is 0, and again, there are 3 of them. So for formality, that's where we get our equation. So we can call them +1, 0, and -1. So mathematically, our formula gives us our 3 orbitals. And it doesn't matter, you know, who's who. So we don't know, right, if this is py, pz, px. It doesn't really matter. We're just showing that there are 3 distinct orbitals. Does that make sense so far? So back to, remember we said that the p orbitals, there are 3 of them. So y is from quantum mechanics, so like the exact answer why, but also, right, the atomic structure. So that's kind of, again, what we've been, right, teasing back out. So we can go back to our electron configuration. Oh yeah, my p was 6 across, right? It's going back and telling us that same information. So, right, this is now my L equals 1 for our p orbitals, right? So we could say they're starting there. My n equals 2 for all of these. I'm kind of following, right? So that matches with your electron configuration with that 2 here. Yeah. Yeah, so this is a p orbital. So this is this what you're asking for? So then we have our p orbitals, right? And then we can compare. So notice that the p orbitals do have a node. So they have 1 node. And so, right, this is going through our characteristics. So again, we have these m sub L values just to, again, correspond. It doesn't necessarily mean that this is always the case, right? We just have 3 to represent our 3. And so, yeah, you were kind of asking, okay, they're 2 lobed, and then the next key point is that there's 1 node at the nucleus, so total of n nodes. So our P has our node there, so of course, right, node on between each one. I'm not sure if I have a graph, because I think I know what you're asking, because did you want to see like the P nested too? I don't know if I have that graph, but it'd be like the same kind of thing, because you'd still have a node then, right? So you have a node between each lobe, but then you'd have another node just like here, right? Where you just have one big node, you would still have a node around each p orbital, right? Does that make sense? So you can kind of visualize that. All right, so then now we're kind of, right, filling in our quantum numbers. So we said, okay, well, L is equal to 2. That corresponds to our d orbitals. And then again, right, think back to the formula for this m sub L thing. So m sub L is equal to, again, negative L with integer values. And so look at how that works out for our d, right? So that means we have -2, -1, 0, +1, and +2 as possible m sub L's. So there are 5 of them, right, which correspond to our 5d orbitals, right? So again, it doesn't matter which one we're calling -2, -1, 0. It's just the fact that there are 5 of them to correlate to the 5 Ds. Does that make sense? And so, right, again, it's shown here. So we can start. So, of course, this is now our third energy level. So our third energy level, we can have 3s, 3p, and, of course, 3d starting there. Again, going through all our combinations. So you can see that, again, 5 of them for 5d orbitals. And again, so we saw that with our d orbitals, that they're these 4-lobe shape. And so now we have, again, more nodes. So we have, right, nodes between each one. And I don't like the shading on this, so they should be shaded like so. Again, through quantum mechanics. And so we'll get to this, but basically things have to have the same shade to bond. So that's why it's important to at least note that there is shading. They'll have shading like so. And then this one, the little donut is a different shading. So our 5d orbitals. And then again, our last one, so our principal quantum number, our L. So L equals 3 corresponds to our f orbitals. And again, right, just going off our formula, that means we have -3, -2, -1, 0, +1, +2, +3, which gives you 1, 2, 3, 4, 5, 6, 7 combinations, right, which correspond to your 7 f orbitals. So not attempt to draw those. And so the rest of this text, again, is just kind of emphasizing now our third quantum numbers, our m sub L. So again, corresponding to our values. So we've kind of seen that. Again, this is a good reference chart. So now we can scroll down. So fourth energy level, right, this corresponds to our 4s, 4p, 4d, and then of course, right, our 4f is invoked there. And again, from our quantum numbers, this is also telling us, yes, this is why F is the first energy level that it appears in, is a fourth energy level, and so forth, right? Going back to all those concepts. And then the last little number is our m sub s. And so that just corresponds to the spin of our electrons. So we mentioned that electrons are usually spin up or spin down. So again, it doesn't matter, it's just a formality. And then we said that, right, we cannot have 2 electrons occupying the same spin. And so this goes back to our quantum mechanics. And so now what we're saying is every electron kind of has to have their unique set of principal quantum numbers such that they can't occupy the same space. So that's where these +½ and -1½ formalities come from. All right, so this is just kind of, again, re-showing us the same information, just in a different format. So put together, again, everything we've been talking about, right? Even going back to our Bohr model of hydrogen. So our lowest energy level, of course, is down here, right? Most negative in energy by our formalities. And then it's written a little different, but again, just kind of get used to these different notations. So we have these little squares with our 2s, of course, is one box, 3 boxes for our 2 p's, and then, of course, right, they could be filled in with little electrons. And so this is just kind of going through all the quantum number possibilities. That makes sense? Questions?
How would you clearly define the M of L? Like, what would you, like, how would you define
The M sub L?
the
So the M sub L just gives the identity of your like sublevel. And so it's also just like a position. And so let's go through some practice. So let's start out with helium. And so let's see if you can determine this. So write out a set of possible quantum numbers for helium. And so they're always given in this kind of x plus minus spin format, right, where the first x is going to be, right, your n energy level, then the next one corresponds to the L, then M sub L, then MS there. So what do we get for this? And before we even write an answer, right, we could think about, well, what's its electron configuration? So helium, right, 1s2. So looking at that, so what's our n, right? What energy level does any electron have to be in? So 1, exactly. And then what orbital does it have to be in for helium? So remember the definition of L, though. Yeah, so 0, right? So maybe go back. I still like this little chart better just because it puts everything kind of, I think, more clearly, right? So now you're looking, okay, we're at N1. Okay, well, what are my options, basically, right? Well, literally only 0, right? Because only the s orbital is allowed. So 0, right, corresponding to our s. And so, right, you can see 0 is S, 1 was P, but obviously we're not there. Oh, I lost myself. So 0. So 1, 0. And then what does M sub L have to be then? So 0, right? So that's based, again, mathematically on those values of negative L to positive L. But again, I like this chart, right? Well, it's an s orbital. There's literally only one option, right? So there's only one s, so it has to be 0, And then what about the last one, M sub s? What's the answer? So not 0. What were the possibilities for M sub s? So what does M sub s mean again? Yeah, the spins, right? So then we only have two options, plus 1/2 or negative 1/2. And, right, it doesn't matter. So we're not observing it, right? We don't know what spin it's in, but yeah, it could be spin 1/2, right? So this could be, this we could say, right, this is for 1 electron. So this is now basically, right, our coordinate for this 1 electron. But then that means, so our second electron for helium would have to occupy this position. And so now all we're saying is, okay, right, we have 2 electrons. Then using our quantum numbers, one of them has a spin of 1/2, one of them is negative 1/2. So again, that's giving us the same information as this, right? Same thing, it's just now we're writing our quantum numbers for this. And right, 2 electrons, they can't occupy the same position, so they can't have, right, they can't both be 1/2. And so that would be like another thing on the exam. Like I could say, okay, well, one helium atom has these, 1 electron in a helium atom has these set of quantum numbers, you know, what is the other allowed set of quantum numbers, basically. So you just have to make sure it has different spins. And then, right, you could also, in theory, right, map out every single electron, right, and give its coordinate. But usually on an exam, I'm going to be asking you kind of where is the valence electron, so give the set of quantum numbers for the valence. All right, so kind of looking through, so again, right, we can recap electron configuration. So same thing, again, everything that we've talked about. So, okay, reminding ourselves, again, the biggest energy gap is between 1 to 2. Each subsequent one is smaller and smaller and smaller, right? We said that as well, even with just kind of our basic oversimplified hydrogen Bohr model. And then this brings up the Aufbau principle, but that's kind of the candy rule. Again, you're just filling in lowest energy level first, and then filling in, right, any degenerate energy levels before pairing. And so we've done electron configuration, right? But then now this is just kind of recapping it. So again, pairing our quantum numbers and how they track with our electron configuration. And so, right, this is all a recap, but now we're kind of seeing, okay, our electron configuration, though, is telling us, right, where these electrons exist, what orbitals and what shape, and all that. And so again, right, we've seen this, and so now we're just kind of recapping our quantum numbers. Okay, right, we're starting with our hydrogen. We could write out our set of quantum numbers, right, 1, 0, 0. Then I'll go plus 1/2, just because they're showing it upright. And so again, now we're getting back into how we got to quantum mechanics and all this probability density. So it says for multi-electron atoms, so basically anything but hydrogen, we can't solve it exactly. And so that's again where we get to our pretty pictures.
So when you have for hydrogen, could it be, if you have plus 1/2, they could equally be
Yeah,
negative for both, right?
yeah. And so, yeah, going back to the spin state starts to, again, that's where you could go back to those forbidden transitions. So, right, you can't be changing spins, but that's beyond kind of this scope. That's where it comes from. And so, yeah, like we saw, again, we have our spin. So that's just, right, our property of electrons. So you can start getting to, like, why are things magnetized, right? So you get all the electrons aligned up. Same thing with, like, NMRs and things that can be affected by magnetic fields. It's because they are susceptible. And so it has to have, be susceptible to, of course, magnetic field. And so again, all this means is that our orientation is quantized, so it's either spin up or spin down. And so again, we saw that for helium, that they have to take opposite spins. So now we're kind of going back around, but we're seeing, okay, from our quantum numbers, now this is reproving to us, again, why they have to be in these opposite spin states, because it is forbidden. And so again, we saw that, so we have our, again, right, so on an exam, it generally doesn't matter whether you pick spin 1/2 or -1/2, just as long as it's not explicitly stated that, right, something's already occupying that position. And so this is, again, just kind of recap, so we're all on the same page. So again, right, writing these little orbital diagrams in various representations. And so spins tend to cancel out. And so meaning, right, that they're paired. So 2 electrons in an orbital must have opposite spins. And so this would be considered diamagnetic. So again, most compounds are diamagnetic. And so again, Pauli exclusion principle. This is where we're saying, okay, well, no 2 electrons in any atom may have the same set of quantum numbers. So again, going back to that, no 2 electrons can occupy the same position. So we saw that with our helium. And so again, this is just kind of going through. We've already filled out the order, right? We can go back to this periodic table to see, again, our electron configuration, right? We went through on the chart how to fill it in. But then these notes are just, again, kind of reminding us why that was so. Again, you're always filling up lowest energy to highest. So obviously, right, that has thermodynamic basis. That's what makes things favorable to form a bond. And so again, right, we mentioned this concept of being degenerate, whether the same energy level. And so you want to fill up, right, each one in the degenerate before pairing. So again, we saw that with carbon, and we could see that, right, with nitrogen too. So just have one more. And so this is, again, where Hund's rule comes into play. Again, just going back to energetics, right? So you have to fill it in. And so again, just kind of recapping. So we have this concept of our core electrons. So anything that's kind of not the valence, right? So the core electrons generally are not accessed versus the valence, right? So this is where all the action is happening. And so eventually, right, that's where we want to get to all these orbitals, and why we care is, okay, well, we want to map out the pretty pictures so that we know what's happening, right? So we know silicon is going to be invoking, right, the 3p then for bonding. And so, of course, right, what we've been getting at is the way the atom behaves is generally dependent on the number of valence electrons. So, right, both we're seeing that it can either participate in bonding or, right, potentially lost. And then, right, when electrons, of course, are added, it's obviously also in the valence shell. All right, let's do, before we do some excited states, let's do some other practice.
I'm sorry, I have one more question. Going back to what you were just explaining, like, does that relate to the, like, when we were looking at in the lab, the valence and
Yeah. So what that was teasing out too was like getting into, like again, the Ds versus the Ps and kind of the reactivity and kind of, again, kind of hinting at the differences in that. So yeah, kind of related, but yeah, the valences is all like an oversimplified approach. And so that's where we want to look at MO theory. So that's where this is going. And so we'll get a baby taste of it, but again, we'll keep working on it. So let's try some exercises like you'd be expected. So let's see. So let's write the electron configuration. For barium and give the allowed set, or unallowed, sorry, give unallowed set of quantum numbers for the valence electron. So how are we doing on this? We have an answer. So let's just start. Well, what do we get for the electron configuration, right? We know that. So what's the electron configuration for barium? So I heard a xenon 6s2. Okay, so I think everybody likes that. So how do we translate this basically to quantum numbers? That's what we're asking. And we're asking about the valence electron, right? Maybe even look at your periodic table with all those numbers you wrote. So then what's the principal quantum number? 6. So, right, good. So, right, and it's shown here, but you kind of have to think back to, right, how we filled it in. So, we had said, okay, right over here starts our 6s. So, yes. That's our 6 for our principal quantum number. And then what's our L? What type of orbital is this? So it's an S. So what's our L then? 0, right? So if it's a S orbital, we know it has to be 0. Okay. And, well, now what's our M sub L, right? We only have one choice. 0. Okay. And then what about our spin? So yeah, plus or minus 1/2. So either answer is correct. And so now we'll play around more with this, but let's kind of look at our last concept before we just stick to practice. And so now we're kind of looking into this excited state thing. And so again, we're just kind of proposing any possibility. And so right in this case, we just took, so we have, right, our 3 atoms here. So this is, 3 electrons for lithium in its ground state. So we can see, okay, 1, 2, 3. And then all we've done is taken this one and promoted it, right, to the 2p. And what the point is, though, is we don't know where it went, right? So again, in theory, it could go anywhere. We're not trying to calculate that right now. All we're saying is it could literally be anything. So when we say, okay, write an electron configuration for an excited state, we can start giving any possibility.
So they have to have opposite spins, right? So if you were to move one opposite to another state, it has to go somewhere that doesn't have the same spin.
Exactly,
So
yeah.
is that why things like the noble gases aren't so excitable? They're so stable?
Well, they actually are very excitable, right? Because they're not reacting when we excite them. They're just being promoted and relaxed back down. So, right, that's where you get like the neon lights. But what we're saying is, right, basically we can predict anything. So, of course, what is shown is, and obviously, right, our ground. And ground just means our lowest energy, right? So just filling in normally, okay, we put our electrons in to the lowest. Okay, so 1s2. 2s1 for our ground state lithium. But then for any sort of excited state, so I'll put excited as shown, right? They just happen to promote it to the 2p. Okay, so 1s2, 2p1. But we don't know where it could have gone.
And as it drops, that's where the energy comes from.
Yeah, so the energy comes in from the relaxation, exactly. But again, right now we're not quantifying that. We're just predicting any excited state. So we could write 1s2, 3s1. That could be a possibility. Yeah. Yeah, why not, right? We don't have any numbers. We can't really characterize that. So yes, for this purposes, just as long as it's allowed, right? So then if you want to put in the F, just put it in the 4F one, right? Who knows? We don't know. You're just writing out any possible possibility, right? And we don't know enough about allowed, unallowed, but, again, probably if it's just one electron being promoted, it's fine. So we don't have to get into all the allowed, unallowed things to worry about. So yeah, so now try this one for a little warm-up, or a little ending. So write an electron configuration for a possible excited state for hydrogen. So what could that be? So anybody want to give any possible excited state?
Push it out to the second S orbital?
Yeah, why not, right? We don't know. So you want to do 2s1?
Yeah.
So 2s1, right? That could be one. What's another possible excited? Yeah. Yeah, so which one do you want to give it? Yeah, 5D1, right? Why not? It's excited. We don't know where it went. Yeah, anyone want to list another one? Yeah.
Sorry,
6F1. Yeah, perfect, right? As long as they're allowed. So that's the only thing. Okay, F starts at the 4, so yes, we can have 6S1. Any others we want to put out there? Yeah. Yep, so 4F1, right? As long as it's allowed. So yes, right? F exists at the 4th energy level. So who knows, right? So you could go on and on, right? As long as it just has kind of one electron. And then like we said, right, again, it's that relaxation of this excited back to the ground state. Yeah. Yeah, why not, right? Again, as long as it's allowed. Yeah.
So that's, you can figure out where it was by measuring the relaxations.
Yeah, so then that goes into, okay, so then we observe the energy, right, the wavelength of whatever transition, and then what the scientists are trying to do and what that book, Atomic Spectra, tries to do is like pair, okay, well, which transition corresponds to which energy?
So it takes more energy to move that more.
Yeah,
right?
yeah,
So,
so
for
bigger
example-
transitions, more energy, but it's also, right, that also
For example,
quantize.
The 4F would be a much more intense wavelength.
Well, not necessarily intense wavelength, right? So that's the other thing is we have to remember the visible region is pretty small. So you could have a higher energy that corresponds to, yeah, like a,
Ultraviolet or.
exactly, a
Okay.
UV transition, yeah. So we only are looking at the ones in the visible region, but yes, there are many ones that are possible, but they just might be too low or too high that we don't see it, but then by an instrument we can measure it, yeah.
Would you say the organics are more likely to make the high?
Yeah, so the
There's a
organics,
sense
that's
that
why they're
the
colorless, because they're all in the UV transition. But then like why the pretty colors, so all the transition metals are pretty colors, because they all have D level transitions that are pretty small and in the visible
Is that why
region.
they burn at different colors, say potassium versus? I
Yep,
don't
so
remember
that's
the colors.
exactly what we're getting into, is why they burn at different colors, so it all has to do, right, with those allowed transitions and kind of what the dominant visible region transitions are, yeah.
Okay.
All right, so yeah, oh.
Those colors are coming from the excited state coming down.
Yeah, so relaxing back down. So we'll do that in lab today, exciting, relaxing back down so we can continue all these conversations. So we're kind of out of time. Lots of good questions. So Thursday we'll keep kind of practicing, make sure this is solidified. And then if you're missing work, come get it. All right. Thanks for being online, everybody. Appreciate it. Again, if anything is funky with your grade, just see me ASAP so we can fix, especially popcorn labs. All right, bye, thank you. I'll stop this.